Good morning, students. Today we are going to learn the topic of pure vibrational spectra of simple harmonic oscillator. According to selection rule, vibrational transition are allowed only between adjacent energy levels. Also, each energy level are separated by equal energy, that is given by delta E is equal to Sc omega E. We also know that E is equal to Sc nu bar. So from this we can write nu bar is equal to omega E. Hence we will get only one line in vibrational spectra of simple harmonic oscillator, which are shown in the diagram. The frequency in wave number of the line correspond to fundamental vibrational frequency. It is important. Fundamental vibrational frequency of oscillator, which is denoted by omega E. At a room temperature, most of the molecules exist in a ground vibrational state. So, nu is equal to 0. Hence, the only transition of interest is from nu 0 to nu 1. This transition is called as fundamental transition, and frequency correspond to this transition. It is called as fundamental frequency. It is important. This is the diagram for vibrational transition and spectrum of harmonic oscillator. So, at a room temperature, most of the molecule lies in nu is equal to 0 state, vibrational state. So, this is a transition from nu 0 to nu 1. This transition is known as fundamental transition, and frequency correspond to this transition. It is known as fundamental frequency. Now we are going to discuss the topic of vibrational energy level in anharmonic oscillator. It is important. In case of harmonic oscillator, the atoms come back to equilibrium position from any distance, but it is not the case with the real molecule, because when we discuss previous topic, we consider it the bond is like a spring, but in actuality bond is not behave as a spring. So what difference it makes? If the two bonded atoms are stretched to the last separation, the restoring force decreases and molecule dissociates. Such a molecule is called as anharmonic oscillator. When we discuss harmonic oscillator topic, we make an assumption that bond is behave like a spring, but in actuality bond does not behave like a spring. If we stretch a bond up to the certain after the certain limit, that bond get breaks and molecule get dissociate. So scientists PM Moore study the effect of stretching on vibrational energy level of the molecule. He put forward an equation called Mohr's equation. Generally, this equation is asked for 1 mark question in exam. It is given by E is equal to D into bracket 1 minus E raised to the power A into bracket R minus R0 bracket close whole bracket square, where D is the dissociation energy of a molecule, R is internuclear distance at any position, while R0 is the equilibrium distance, which is shown in this diagram. When Schrödinger wave equation was solved using the value of potential energy, the vibrational energy are given by this equation. That is E nu is equal to into bracket nu plus half Sc omega E minus into bracket nu plus half whole square multiply by Sc Xe omega E, where Xe is called an unharmonicity constant. Now this term is of our interest. It can be seen that separation of two energy level is less by this factor as compared to harmonic oscillator. So as the value of nu goes on increasing, the separation goes on decreasing. Hence the energy levels are not equally spaced, but they fall closer as energy increases, and finally energy becomes continuous, just like this. In this diagram we see that as the distance increases, energy become continuous. Just see the potential energy y-axis above this distance, we see that the value of potential energy is continuous. So in case of anharmonic oscillator, the selection rule is also changes. So selection rule for anharmonic oscillator is delta nu is equal to plus minus 1, plus minus 2, plus minus 3, etc. are allowed. Thus various transitions are possible from 0 to 1, 0 to 2, 0 to 3, etc. Hence we get different bands in the spectrum. Most intense band is for the transition nu is equal to 0 to 1, because greater the population of molecule are in nu 0 level. This intense band, it is important, is called as fundamental vibration band. The absorption correspond to this band is called fundamental absorption. The weak intensity band correspond to transition nu 0 to nu 2. Extremely weak intensity band correspond to transition nu 0 to nu 3 is called second overtone. For nu 0 to nu 2 it is called first overtone band. So this is the diagram given for anharmonic oscillator. And the dotted diagram is for your energy curve for simple harmonic oscillator. So just see that in simple harmonic oscillator, it goes up, this line goes up. It means that as the value of nu increases, potential energy increases simultaneously. But in case of anharmonic oscillator, we see that potential energy increases up to certain level, then it becomes continuous. Why it become continuous? Because of this factor. Now we are going to discuss vibrational rotational spectra. Pure vibrational spectra can be observed only in a liquid, where rotational motion is inhibited by intermolecular interaction. In case of gaseous state, the molecules are rotating continuously irrespective of their vibrational state. The energy required for rotational transition is extremely small as compared to vibrational transition. Hence, vibrational transition are invariably accompanied by rotational changes. Such a gaseous molecule give vibrational rotational spectra. So, we are basically going to discuss vibrational rotation spectra of gases. So the energy of vibrating rotor is given by the sum of vibrational energy and rotational energy. So E of nu comma j is equal to E of nu plus E of j. But we know that energy is equal to Sc nu bar. So by using this formula, we can write this. So V comes nu bar V comma j is equal to nu bar nu plus nu bar j. So V comes with this equation where nu bar Vj represent wave number of energy level given by vibrational quantum number nu and rotational quantum number j. When vibrational transition is accompanied by rotational transition, the selection rule is given by delta nu is equal to plus minus 1 and delta j is equal to plus minus 1. Since most of the molecules are in ground vibrational state, consider vibrational rotation transition from nu 0 to 1 accompanied by rotational transition j to j dash. The wave number corresponding to this transition is given by this equation. After solving this equation, we comes with this equation, that is delta nu comma j is equal to omega 0 plus times b into bracket j plus 1. If we put the value of delta j is equal to plus 1 into this equation, if we put delta j is equal to minus 1, we got this equation. Just see the difference in between these two equations, that is, this is equation A, let this is equation B. So for delta j is equal to plus 1, we clear cut see that here is a positive side, into bracket there is j. While for delta j is equal to minus 1, we clear cut see that it is the minus sign and into bracket there is j dash. So now we are going to discuss appearance of vibration rotation spectra, that is PQR bands. So vibrational rotational lines are obtained at the position given by these two equations. Following important conclusion can be drawn from these two equations. No line will be obtained at wave number omega 0. This wave number is called band center or band origin. This frequency is also called as fundamental frequency. Putting the value of j is equal to 0, 1, 2, etc. get various equal space line with a spacing twice b. For delta j is equal to minus 1, lines with a lower frequency than fundamental frequency are observed. This group of lines is called as pre-branch of spectrum. For delta j is equal to plus 1, lines with higher frequency than fundamental frequency are obtained. This group of line is called as R branch of the spectrum. For delta j is equal to 0, that is for purely vibrational spectrum, get the line at fundamental frequency. This group of line is called Q branch of spectrum. This branch is not observed in vibrational rotation spectrum. It is important. This branch appears only in purely vibrational spectrum. So we are going to see what is PQR branches in a spectrum. So intensity of P and R branches goes on increasing on either side of Q branch and then decreases. So just see here, this is known as Q branch of the spectrum. This whole sector P1, P2, P3, P4, P5, P6 are known as P branch of the spectrum, while this right hand side is known as R branch of the spectrum. Now the value of P branch of the value for P branch lines of P branch of spectrum is always less than your fundamental frequency, while the values for lines of R branch of spectrum is always greater than value of your fundamental frequency. In our next topic, we are going to discuss application of vibrational rotation spectra. Thank you very much.